By the way, I don't look at the chat. My screen is my mic off? I thought, okay, I think, can you hear me? I think the mic is off. Okay. I got a response from Ali. I totally agree. So he understood what I was talking about. Okay, anyway. So the first thing I'm going to do is to look at the question that I proposed last time. Remember, last time we talked about the Larmor relationship. We talked about actually production of X-rays. We talked about characteristic X-rays, and then we looked into Brabantse X-rays, and we said, okay, the Brabantse X-rays, they are the rate or the power emitted follows the Larmor relationship. So if you remember the Bohr model, one of the assumptions is that X-rays or the electron does not emit any electromagnetic radiation when it is in orbit. And while it is in orbit, the electron revolves and therefore there is an acceleration. So from classical electrodynamics, an accelerated charged particle is essentially going to lose energy following the Larmor relationship. By the way, this is the classical Larmor relationship. There is a relativistic one where there is a gamma to the power 6 somewhere there. So the question is, okay, suppose that we forget about that postulate and we just use the classical electrodynamics and the Larmor relationship. So we want to ask if we can estimate how long does an electron in a hydrogen, in a ground state hydrogen atom, would it take for it to collide with the nucleus? So while it is accelerating with the Coulomb force, it's going to emit radiation and it's going to lose radiation. Okay, so following the Larmor relationship describes the power of radiation that is emitted. So since we're talking about the electron, then the loss of energy is using the Larmor relationship, but there is going to be a minus sign there. So the solution, this is the Coulomb force. The Coulomb force is, we're using classical formulas. The Coulomb force is given by the mass times the acceleration, and this is the magnitude of the Coulomb force between the electron and the nucleus. So from this equation, we can actually solve for A. And so this is one parameter we need to get, okay? So A, and the total energy is the sum. Because now we want to look at what's the rate of this changing energy. So the total or the electron total energy is the sum of its kinetic energy and its potential energy. So the kinetic energy is just 1/2 the mass times the velocity squared, and this equals to 1/8 pi r e squared, using just solving from here what is V or V squared with respect to the Coulomb force here. So, and the potential energy is given by -1/4 pi epsilon 0 e to the e squared over r. So this is now, we add the two energies, the kinetic energy and the potential energy, and at the end, we get that the energy of the electron, the total energy given by minus e squared over 4 pi epsilon 0 1 over r. So we're going to use this formula and plug in the information. All what we need now is dE. Okay, so this formula is E. We need dE. We need to differentiate with respect to R to get dE over R or d over t, and we end up with this big formula here. The point is that this is, all of these are constants, and then this rate is going to be -1/r to the power 4. Okay, so using the relationship between R and E, okay, again, we end up with a formula that looks like this. So this is like a constant dt, and then we integrate with respect to the energy from energy, Bohr energy electron, which is minus 13.6 electron volts, or up to minus infinity. So this is the integration, and we get the formula. We evaluate with these limits from initial energy being minus 13.6 and the final energy equals to minus infinity. Okay, so at the end, this is the time for the collision of this electron. And it is going to be about 1.4 times 10 to the power minus 10 seconds. So essentially what it means is this: if this electron is emitting radiation following the Larmor relationship, the hydrogen atom would not exist actually. Okay, so that's this is the solution of that question. Okay, so we're going to start today's lecture. So let's see if I can share or do this. I want to fix something here. Okay. So today we're going to talk about X-ray spectra from targets. So before we start, I think it's important to understand some of the definitions we find in textbooks or this version. For example, what's the particle fluence? We have energy fluence and so on. So the particle fluence, it is defined as the number of particles. So let's imagine we have a sphere here, and with a cross-sectional area of A. So essentially, all what we're doing is we're going to count how many particles are going to cross this cross-section area. So the particle fluence is defined as the number of particles and crossing an imaginary sphere of cross-sectional area A. If the particles, all of these particles, are monoenergetic, they have the same energy, then the particle fluence is given by just the number divided by the area. For an SI unit, the SI unit for particle fluence is per meter squared. The number of particles, of course, it does not have units. So you can put particles per meter squared, or the SI unit is just per meter squared. Now, following that trend, we can define what's the particle fluence rate, and this is often called particle flux. So the flux is a rate. So it's a fluence rate. Flux is basically we replace the two words of fluence rate with flux. So it's defined as the number of particles crossing an imaginary sphere of cross-sectional area A per time t, okay, or per unit time, or in delta t. So for a monoenergetic beam of particles, the particle fluence is given by the derivative of the particle flux. Sorry, this is the particle flux is given by the derivative of the fluence. Okay? And again, we can write it in such a way. And the SI unit for particle flux is therefore going to be particle per meter squared per second. Now, this is a concept that I think a lot of people struggle with, is basically when we talk about the density, particle fluence density. So for a beam of particles, so now we have this is used to describe fluence, but not for a monoenergetic beam. It's used for when you have particles with different energies. So for a for a beam of particles with different energies, we're going to define this quantity, the differential particle fluence, or sometimes it's called the particle fluence density. Density is not per volume. Don't think of density of volume, but it's per energy. It's given by this quantity here, where basically what we need to do is count how many particles with energy E crossing that cross-section area, A, or basically it's the number of particles with energy between specific kinetic energy plus DEK. Okay, so we count or we look at a range of energies. And of course, we'll select DE to be as small as possible. So in order to give us the particle fluence density. And the SI unit for the differential particle fluence, in this case, is going to be meter squared per joule. Okay, because we have this basically particles, we have the area, SI unit for it is meter squared, and DE is in joules. That's the energy in joules. Why this is defined like this, in order that, okay, before we move to that point, we can continue defining the particle flux density. It's the same definition, okay, except that now we're looking at the rate of these particles crossing, having energy between E and DE, crossing that cross-sectional area A. And the SI unit for the differential particle flux is then going to be meter squared. Here, this is the rate, so we have per second, and here we have energy, which is per joule. So it's going to be meter minus 2, or per meter squared per joule per second. Now, the reason why we define the particle density is essentially we can use that density to if we integrate it over all energies of the particle, then we will retrieve or calculate the total particle fluence. So the total particle fluence, then, if we have a spectrum, is then given by the particle fluence density integrated over all energies. So here the integration limits, obviously it's going to be from the minimum kinetic energy of particles to the maximum kinetic energy of the particles. And again, the total particle flux is basically the integration of the particle differential particle flux or the fluence density. I mean the flux density. We integrate over the flux density in order to get the total number of particles crossing that cross-sectional area. Now, using these two concepts, we can then start to calculate, okay, what's the mean energy of the particles? So particle fluence, we're going to average the energy over the particle fluence. Or this actually should be the particle fluence density. We're averaging over the particle fluence density. So therefore, the energy or the mean energy is then we take this particle fluence density multiplied by the energy, take the integration, and then we divide by the total particles. Essentially, you can think of it as we are counting particles, summing up their energies, and then we're dividing by the number of particles. But this is how it is written in integral form. Now we move to another concept, which is actually more important for us, is the energy fluence. So now, usually we're not interested in how many particles are crossing this cross-sectional area. We rather would like to look at the energy of these particles that are crossing this cross-sectional area. This will become apparent when later on we would like to calculate, for example, the dose from a beam. So for more energetic beam of particles with energy Ek, then the energy fluence is given by the energy, the total energy crossing this sphere, okay, divided by the cross-sectional area A. So if we have a monoenergetic beam, then all what we need to do to determine the total energy crossing is we take the energy of the particles multiplied by the number of particles. And essentially, this is basically the energy times the particle fluence. So the energy fluence for monoenergetic beams is just the energy of the particles multiplied by the particle fluence. This, remember, this represents the total number of particles crossing that area. Now, the SI unit for the energy fluence is therefore going to be joules. That's the energy divided by the cross-sectional area, which is in meters squared. The energy fluence rate, again, is just the rate of these particles for monoenergetic beam is going to be the energy rate crossing this cross-sectional area. And essentially the fluence rate or the energy flux is going to equal to the energy of the particles multiplied by the particle flux. And now the SI unit for energy flux is therefore going to be given by joule per meter squared per second. Now this has a special name. When we talk about the energy flux, we usually define that, we call it the intensity of the beam. So whenever you hear the beam intensity, okay, it's not really talking about the number of particles, it's talking about the energy that is going through a specific cross-sectional area, okay? So that's, and intensity, it's the rate of energy then. It's going to be the rate of energy crossing that cross-sectional area. Now, following the same steps, defining an energy, a particle fluence density, we can define an energy fluence density. So, or sometimes it's called, or differential energy flux is given by this relationship here. Okay. Where basically, again, what we need to do is we look at a specific energy window, for example, from E up to dE. And then we count what's the energy that is carried out by these particles, having an energy E between E and E plus dE. The SI unit now for the energy fluence density is meter squared. Okay? So although the energy fluence is has an energy has a SI unit of meters joules per meter squared, now the energy fluence density actually has an SI unit of per meter squared. And again, we can define the energy flux density is we take the derivatives, okay, of this. Is basically we're talking about the rate of energy for particles with energy E between E and E plus dE that are crossing that sphere or the cross-sectional area A. And the SI unit for the energy flux is therefore going to be per meter squared per second. Okay, this is always sometimes confusing to me because now we're talking about when we usually look at the fluence, okay, we think, okay, it's energy fluence, it should be meters, joules per or energy divided by area. But when we're looking at the energy fluence density, then it is it's just per area. Because we're going to integrate over all energies. Now, the total energy fluence, again, is just the integral of the particle or the energy fluence density. We integrate it over all energies from E minimum energy of particles to the maximum energy of particles. And we can actually calculate now in a different way the mean energy, but now we're going to use the energy fluence. And they are different. I'm going to show you an example between the two. So the average fluence for a beam, this is the average energy, sorry, average energy for a beam, averaged over the particle fluence is given by, again, we integrate that energy fluence density. We multiply, so that's the basic, that's the main quantity. If we want to take an average with respect to energy, we multiply the energy by the fluence density, and we integrate and divide by the total fluence. Okay, this essentially will give me the mean energy of particles, but averaged over the energy fluence. So here is an example. So imagine we have a differential particle fluence of a photon beam given by the following relationship. This is essentially a straight line, okay, between photon. So we're talking about photon beams here between 0 up to 1 MeV. If we plot it, basically, this is now the particle fluence density of the beam. That's the equation of the beam, okay? Here we have the energy, and here we have the particle fluence density in MeV centimeter per MeV per centimeter square. So essentially, the first part, if we want to know what is the total number of particles using the particle fluence density, it's basically we integrate over this curve. So we take the area of this curve. We can use the integration formula, or if we look at this, so it's a smart, this is a triangle, then it's the base multiplied by the height divided by 2. So that will give me the area of under this curve. So anyway, I like always to go with the difficult methods. So this is the integration. We integrate this formula, and at the end, we get the particle fluence equals to 1.5 10 to the power 5 per centimeter squared. Again, the units of the total particle fluence is going to be per centimeter squared. What is the mean energy that average over the particle fluence? We're going to utilize this formula. This is here now the particle fluence density. We multiply first by the energy and take the integration of this. And on the bottom here, we just need the total particle fluence, which we already calculated in the previous slide. So we perform this integration, and then at the end, we will get that the average energy of photons averaged over the particle fluence is going to be 1/3 MeV. So remember, when we have this straight line, the average, when we average things out, the average will be at 1/3 of the maximum of the base. Okay. So using the particle fluence, we can calculate the energy fluence. All what we need to do is for every point here, we just need to multiply it by the energy, okay, using the formula. So we do this, remember, this is a straight line, we multiply it by the energy, we get like a parabola shape. This is now the energy fluence density. This is the energy fluence density. We can then calculate the total energy of particles, or total energy fluence by just integrating, sorry, the previous slide, this is actually the energy fluence density. Yeah, it's not the energy fluence, it's the energy fluence density. Then we integrate the energy fluence density with respect to a photon beam from 0 to 1 MeV. We do the equation here, okay, and then at the end we will find that actually the total energy fluence is given by 5 times 10 to the power 4 MeV per centimeter squared. So now let's calculate what is the mean energy. But now we're going to use the energy fluence. We're going to average this, determine the mean energy, average over the energy fluence. We utilize the formula, and we do the integration. And at the end, we will find that actually the average photon energy averaged over the energy fluence is actually going to be 1.5 MeV. So they're not the same. So when we talk about the average energy of the beam, are we averaging it over the particle fluence or under the energy fluence? It makes a difference between the two. Okay, and this is an example that demonstrates this. And if we look back at the curve, well, the average over this line is about 1/3 of the space. So that's the mean energy is going to be 0.33 MeV. Now, if we use this curve, the average is then going to be 0.5. And I think it's obvious from the two curves that the two averages are different. So the bottom line, what I wanted to demonstrate is when we talk about the average of photon beam or average mean energy, we have to think, are we averaging over the particle fluence density or averaging over the energy fluence density? It makes a difference between the two. Now, in practice, when we talk about the average energy of a beam, it is actually based on the energy fluence density, not based on the particle fluence density. So the average energy of a beam, don't think, okay, we're going to sum, for example, all the energy and then divide by the number of particles. That's not typically what we use when we define the average energy of a beam. It is actually based on the energy fluence or energy fluence density. So now that's just a quick review of some of the definitions. So now we're going to talk about the spectrum, actually, what's going to be expected when we use, for example, electrons, they shoot or they hit a target. So the interactions of these electrons as they interact with an atom or the atom of a target. So we're talking about one single atom. So we can have X-rays produced from electrons. We will have Brahmi-Shalan. So this is, for example, an electron directly hitting the nucleus. It's going to probably give me the maximum Brahmi-Shalan energy, or the energy of the Brahmi-Shalan that is going to be produced actually ranges from 0 all the way to the maximum energy or the energy of these electrons. So the maximum photon energy will probably be produced when we have such a direct impact or a direct hit on the nucleus. Now, if the electron had, there is an impact parameter B that is not 0, then the energy, so the electron as it approaches or comes close to the nucleus, then it's going to be deflected. Okay? And the energy of the photon that is emitted will depend how much was this electron being deflected and so on. So here, for example, this second electron, okay, we're getting an intermediate energy, Brahmi-Shalan energy. This is going to give me the maximum. This is a moderate or intermediate, and this one just had a slightly or a small deflection. Then the X energy of X-ray that is going to be produced is of low energy. So this is now when we're talking about an atom. Just a slide from the previous lecture. This is the Larmor relationship, okay? And the important thing is that Brahmi-Shalan is produced when we're using electrons, heavy charged particles do not contribute or Brahmi-Shalan, I mean, they're very, very low and usually we neglect them. And that based on Dwayne Hunt law, the photon energy emitted can have an energy, a maximum energy, which equals to the kinetic energy of the electron, all the way down to 0. We've also talked about the direction now of the photon, where it's being emitted, and it has this characteristic angle of this gives me the maximum intensity or maximum intensity of photons. So for example, if we have a low energy electron, this is the intensity of photons as a function of theta. We'll find that the maximum intensity will be produced at 90 degrees, and probably in the forward direction, we will have no electrons, no photons at all. This is just for a single interaction. Whereas if we have a high energy electron, so here the kinetic energy of electron is 1 MeV, we'll see that the characteristic angle is more in the forward direction. Here in this example is at 10 degrees. And this is another plot essentially stating the same thing, but now we don't have a single electron. We're talking about an electron beam, not only one interaction. So the previous slide, this talks about a single interaction. Whereas in this slide, we're talking about a beam of electrons hitting this target at low energies, at here at 10 kV, 100 kV. So this is the potential. So essentially the energy of the beam will be 100 keV of the electrons. Then this is the direction of intensity. And as we increase the electron beam energy, here it's for 20 MeV, okay? Or so the electrons in this case will have an energy of 20 MeV. We see that the distribution of the X-rays more in the forward direction with respect to the electron energy. And this, I think, now is obvious to all of you, how or why we construct, for example, an X-ray tube in such a way, the target and the beam with respect to the patient, whereas in a linear accelerator, where we're interested in producing megavoltage beams, the electrons are actually shooting towards the patient. So we put the target between the electrons and the patient. So imagine now, so now we want to look at, we've talked about the angles, but now we want to look at the energy distribution of these photons. Okay. So the idea is that, imagine that we have a thin target, a very thin target. The assumption is that in this thin target, the electron is going to generate one photon, and that's it. So the electron is not going to interact multiple times. This electron is just going to generate one photon from this thin target. The energy of this photon will be maximum energy would be matching or equal to the kinetic energy of the electron. This is if the electron, for example, had a direct hit with the nucleus all the way down to zero. So the photon energy that is emitted from a thin target, it has these energies. It's not, they will not come out with the same energy, but will have a spectrum. Okay, different energies. Maximum is going to equal to the kinetic energy of the electron, and minimum obviously is going to be zero. Now, for such a thin target, the differential energy fluence or the energy fluence density is constant for these targets. What does this mean? It means that if we plot the differential energy fluence, remember, what we're talking about is how much energy carried out by a certain photon interval. So for example, if we're going to look at the number or the energy carried out by, let's give an example. So suppose we have a 100 keV electron. The photon energy, for energy that could be produced would range from 100 keV, that would be the maximum, all the way down to zero. Now, if we look at the energy fluence of the photons being emitted from this thin target, we will find it's a constant value. What does this mean? It means, for example, for every one photon produced of 100 keV, we're going to have 100 photons with energy of 1 keV. Because the energy, remember, the energy fluence is constant, meaning that 1 MeV photons produced, if we have one, then the total energy is going to be 100 keV. If we looked at the photons produced with energy of 1 keV, then we need 100 of these photons in order that the energy fluence matches that for the 100 keV. So this is basically the assumption. I think it's also by Duane and Hunt that the energy fluence for photons produced in this thin target, it's a constant value. This is how it looks like. This does not mean that we will have the same number of photons or a constant number of photons. That doesn't mean this. Okay, it doesn't mean that we're going to have one photon with energy 100 keV and one photon with energy 1 keV. No, it means that the energy carried out by 100 keV photons is going to equal to the same energy carried out by 1 keV photons. So then we will need 100 of these of 1 keV photons for every 1 MeV, for every 100 keV photon being produced. Okay. In reality, we don't use thin targets, we use thick targets. So the way we approach this is, okay, let's think of this thick target made out of small number of thin targets. So if we have an electron in the first thin target, it's going to interact, producing photons, and the photons produced from this first layer is this in the base here. Okay? So that's the fluence, energy fluence of these photons. Now, as the electron moves to the next layer, it's going to lose energy. This energy is going to be lost either through collisional interactions. That's something we're going to talk about when we deal with interactions of electrons, or the Bremsstrahlung that is emitted. But the point is, as this electron moves and reaches the second layer, its energy decreases a little bit. Now, in the second layer, the energy fluence produced by this electron, again, it's going to be constant. But now the maximum energy is going to be less because the electron, as it entered this second layer, had an energy less than when it started, it approached the target. So the fluence from the second layer is going to have, still going to be constant, but it's going to have a lesser value of maximum energy. And you can do this for the third and the fourth and so on until the electron stops in the target. So essentially, what we're going to have, think of these are made from different layers. Then each layer, of each of these thin layers, they will produce a constant energy fluence with a maximum energy that will depend on the electron energy when it entered that particular layer. And we will stack these fluences on top of one another. And essentially, we're going to get more like a straight line like this. Okay. So this represents the spectrum of photons produced in a thick target. Okay. This is in a thin target, and this is in a thick target. This is essentially a straight line. Okay. And we can actually represent the fluence density. Okay, this is now a fluence density given by an equation of a straight line. This will depend on the maximum energy of the electron as before it hits the target, minus some energy, and then we have a constant, and this will also depend on Z of the target. And remember, in the Larmor relationship, if we go back, we have the power is I think it's Q is the charge, the charge. It will depend actually. I don't know if I have the slide, but I think in the previous slide we talked about it, that the Larmor relationship, essentially it depends for the target, not for the particle. This here talks about the particle, and the target, the acceleration will depend on the target material and what we said, and the mass of the particle. This acceleration will depend on the mass of the particle and the atomic number of the target. And we showed that this is actually going to be proportional to Z. The acceleration is, or acceleration square is proportional to Z, whereas it's actually inversely proportional to M squared. Okay. That's why the fluence or the energy fluence density, it's going to be proportional to Z of the target. This is not Z of the particle. We're talking about electrons, Z of the target. So here is an example of this Brahma-Sharang spectrum. Okay, and if we look at the unfiltered Brahma-Sharang spectrum, it should follow this line. And this is the maximum energy, because the potential used to accelerate, the maximum potential used to accelerate the electrons is 90 keV peak. So the maximum energy we're expecting photons of the photons coming out will be 90 keV. But the fluence density of the beam, it's going to follow this straight line, and it's going to, this could be described by this linear relationship. Now, in reality, when we have a thick target, although we have actually these low energy photons being produced in the target, but these photons, essentially, they will be absorbed again by the target. They cannot leave the target. There's such low energy photons, they will be absorbed in the target. And this is actually, if we conduct a measurement of these Brahma-Sharang photons, it will not follow this straight line. This is like a theoretical value, okay? But essentially, we're going to have a filtered Brahma-Sharang spectrum. All of these low energy photons, essentially, they will be absorbed in the target. Only those with sufficient energy, they will come out from the target and they will contribute to the beam, the photon beam emitted from this target. Okay, so that's the difference between an unfiltered. Unfiltered is a theoretical fluence density. It's just a energy fluence density following this straight line. Whereas in reality, the beam that comes out will be filtered. It will, some of these photons will be attenuated. So if we look at the stick target, in this first layer, we're going to actually have low energy photons being produced. And in that case, these low energy photons, probably they will be attenuated. They will not come out from the target. So what we're going to observe here are probably only these higher energy photons. The low energy photons probably will be absorbed within the target. That's why this is what we get then later on, is this filtered Brahma-Sharang spectrum. Now the filtration could happen, for example, in a typical X-ray tube. We will have filtration from the target and probably from the tube window also. What comes out from the tube window will be filtered. And in diagnostic, this is also an approach, is that they can add, or additional filtration is actually added from the beam. And when we add an additional filtration, all what we're doing is we're just decreasing these lower energy photons. We're definitely, the overall energy fluence that comes out is going to decrease, but we are decreasing more of these low energy photons. These in diagnostic applications are useless. Essentially, they all what they do is just deliver or give the patient a higher dose without really any contribution to the image itself. That's why usually additional filtration is going to be added. What's really interesting is that whenever you have filtration, what essentially we're doing is we are also, although we're decreasing the overall energy fluence, we're increasing the mean energy of the beam. So for this unfiltered, if we look at what's the mean energy for the unfiltered, said it's going to be 1/3 of this maximum. So probably it's going to be around 33 keV. Okay. For the filtered, no, the average energy is going to be a little bit higher. It's going to be higher than that, and one needs to integrate this energy fluence density curve to get the mean energy. But I think it's obvious that the mean energy for curve 3 is going to be higher than the mean energy for curve 2. And essentially at the end, if we add more filtration, we are just decreasing the energy fluence coming out from the beam, but what we're gaining is that we're increasing the energy of the beam. So the mean energy for curve 4 is essentially going to be higher than that for curve 3 and for curve 2. So unfiltered and filtered spectrum. Unfiltered Brahms-Salang spectrum shows a ramp shape or a straight line. It's a relationship between the energy fluence and the energy of the X-ray produced. The highest X-ray energy is determined by the maximum electron energy. So example, the voltage in kV peak applied across an X-ray tube. Usually we use the kV peak for X-ray tubes because the potential is not constant. The potential ripples. Okay? So we're looking at the peak potential there in X-ray tubes. The filtered spectrum shows distribution of no X-rays below a cutoff energy. That is determined by the degree of filtration of the beam. The more filtration we add, this cutoff energy is going to be higher. So essentially, below that cutoff energy, we're not going to observe photons with that energy, or at least it's going to be very, very low. Example, in the curve we showed previously, this is, it was roughly around 10 keV. These low energy X-rays, they are absorbed in the target or any filtration coming out added to the beam. And what's happening is that the average X-ray energy typically for a filtered spectrum is not going to be 1/3, but usually it's going to be between 1/3 up to 1/2, something like this. Okay, so it's a little bit higher than 1/3, although I know this is something we, as a rule of thumb, what's the main energy of an X-ray, of a beam of coming out from an X-ray target. We look at the maximum, we say it's about 1/3. It's actually a little bit higher because of the filtration. This added filtration will happen, okay? Now, when the electrons, they interact with with an atom in a target, they can actually give an orbital electron energy. And this electron, this orbital electron could be knocked out. Here in this example, an electron is just collided with this K shell electron, and this K shell electron obtained sufficient energy to escape the atom. And then a vacancy will be created. And we all know now, whenever there is a vacancy created, both processes will begin. So we will have relaxation of the atom, meaning that electrons from higher orbits will come down and fill that vacancy in a lower orbit. When this happens, one of two things are going to happen. Either emission of a characteristic X-ray or OG electrons. And that probability will depend on the material itself. Remember that curve, the fluorescence yield we talked about will depend on the target material as well as on the shell from which this vacancy was created. But the point I want to emphasize is that these photons that are characteristic photons, they will have specific energies. It's not like the Brahmi ranging from here to here. No, these photons will have a specific energies, and we talked about this, the K alpha lines, the K beta lines, we have the L alpha lines, L beta lines, and so on. So these characteristics X-rays are also going to be produced from this target. They will be produced. So in an X-ray beam coming out from a target, we will have two sources. We will have Brahmi photons, and we're also going to have the characteristic X-ray photons, and these are characteristics of the target. When we look at the spectrum coming out, we can essentially determine or know, if possible, I mean, we can know what is the target actually that is used to produce this spectrum, photon beam spectrum. We cannot do that from analyzing the Brahmi photons. We can only do this from using these characteristic X-rays. So this is what we talked about last time, the X-ray line spectra. These are transitions. We talked about forbidden and allowed transitions. And essentially the highest energies of photons, or the most probable, we're going to see these lines, the K alpha 1 and K alpha 2. These are transitions from L2 and L3 energy levels down to the K energy level. These are the two alpha lines. Although I think the figure that I used, something is wrong in it, because my understanding is that when we say K alpha 1, 1 represents the highest energy. So if we look at this, I think these are labeled vice versa, because the highest energy is this. So this should be actually the K alpha 1. Here it's written K alpha 2. Anyway. So this, okay, I went all the way to the first slide. I actually had it here. So this is a filtered spectrum of Brahmi in addition to the characteristic X-rays produced. So here we see, for example, the K alpha 1 and K alpha 2 lines. This is a tungsten target. Since it's tungsten, these are going to be roughly around 58, 59 keV. Okay. And here we have the K beta 1 lines and so on. The L alpha lines are very low in energy. And sometimes these are going to be very difficult to actually see in a target, because essentially they will be absorbed, filtered either in the target or in any filtration beyond the target. So although they are produced, we're going to have L alpha lines, L beta lines, but these are at very low energies here. Okay. So this is the last slide for today. Okay, but I really want to have, I thought since no one is solving questions, well, I'm going to ask actually questions. Okay, and let's see if the basic concepts you have grasped or not. So the first question is, okay, what's the effect on the intensity of a beam if the applied voltage in an X-ray tube is double? So now we put for example, the potential in an X-ray tube, or the KV peak, suppose was 80 kV. Now we just turn the knob. We still have the same current of electrons, but we increased actually the potential difference between the cathode and the anode. And now this potential difference is 160. So the question is, what's going to happen to the intensity of the beam? Are we going to get more energy out? Are we going to get less energy out? Or the energy fluence, is it going to be less? Is it going to be more? Or it's going to be equal? So anyone has a answer for this? Difficult question?
Well, I have.
It's not difficult, but I think doubling the voltage. I'm not sure, but it's something related to the 15% rule. Doubling the voltage, it's like doubling the intensity.
Doubling the voltage
Yeah.
means doubling the intensity. Who agrees with this?
It's increasing intensity either way, but I'm not sure if it's doubling or not.
معلش أحد من محمود, if you can look at the chat, because honestly I don't have my glasses, I cannot read well, and I'm not following what people are chatting. Okay, someone is writing. Okay, Mahmoud, actually you were writing in the chat. Okay, 4 times. Okay, so we have an answer.
في برضه في زاد وطاقه اختراق الفوتونات تزداد في حاله ازدياد الفولتج. هو انت ازداد فعلا بس ما قالش النسبه قد ايه يعني.
Okay, now we agree it's going to increase. So roughly, how much is the energy output going to be if we double the voltage? Okay, so just now, Marwa, I think now you're not going to forget this. We said this is how the Brahmacharya looks like. Okay, this is the maximum energy. This will depend on the voltage. Okay, it's the energy. And the intensity essentially is just this area. Okay, the total intensity of the beam, what's coming out, is that area. Now imagine what's going to happen if we double this voltage. Here, we put it here. Again, we have the same target. Okay, in that equation, that straight line equation that we talked about, this is going to be like this. Okay. So now, let's convince you. Let's look at this, and let's look at this. Okay. Of course, my drawing is not to scale, but you will find that this triangle, this area, equals to this area, and this area, again, equals to this area, and this area, again, is going to equal to this area. So initially, this is our intensity. Now we have 4 times the intensity. What's coming out is 4 times more. Okay. So this intensity, okay, is actually proportional to the voltage squared. Intensity is energy fluence, or we can talk about it as the energy fluence rate. It doesn't matter. Okay, but this intensity of, so doubling the voltage increases the intensity by 4 times. Now, this is, of course, the theoretical part, assuming that, okay, we have an unfiltered beam. Now, if we have a filtered beam, probably it's going to be a little bit less than that. But this is what we usually, because what we now need to understand is, okay, these rules of thumb. What happens when we do this? What happens when we do this? By how much does it increase? Okay, it's not linearly proportional. It is actually proportional to the square of the voltage. This voltage, remember the voltage determines what's the kinetic energy of the electrons. So we have in an X-ray tube, we have this, we have the cathode, and then we have the anode here. Okay. And essentially, we're putting a voltage across these two. So the kinetic energy of the electron beam, when it strikes the target, is just going to be E times the voltage. So the electron beam, or the electrons, when they strike the target, they will have an energy of E multiplied by the voltage. So if we put here, for example, 100 kilovolts, that's the potential, then what we're expecting is that the electrons, the kinetic energy of the electrons, when they hit the target, is going to be 100 keV. That's their energy. If we double the voltage, then the energy of the electrons is going to be double that. It's going to be 200 keV. So this is with respect to the electrons hitting the target. Now, when we look at the spectrum of photons coming out, this is going to be the spectrum of, imagine this is the 100. The maximum energy of photons is going to match the maximum, or the energy actually of the electrons, 100 keV. And if we increase the electron energy, then the maximum energy of the photons is going to be 200 keV. And the intensity is therefore proportional to V squared. Of course, here we're ignoring the filtration issue, because typically this is going to probably look like this. Okay, clear?
Yes, clear. So I just I want to
So
ask.
this is something in a board exam. This can come, okay? What happens, to the intensity, or the intensity proportional, for example, to the voltage squared, to the voltage to the power 4, things like this. We need to now understand what's going on. Okay?
Yes.
Okay. Let's move to another question. محمود تابع الشات. Okay.
متابع دكتور لسه ما فيش
Okay.
حاجه.
This is a different question. Okay, what is the effect on the intensity if a lead target is used instead of tungsten? So imagine we have a lead target, we had a tungsten target, we're getting a certain intensity, or we're getting a certain spectrum. And we integrate over that spectrum, then we get the intensity. The question is, what happens to the intensity of the beam if we replace this tungsten target with lead? What's going to happen? Is it going to remain the same, or the intensity will increase, or the intensity will decrease?
I think the intensity will increase.
Okay.
Depends on this the Z number of في التنجستن أكبر من الليد.
طيب احنا كان tungsten وحطينا lead. Why is it going to increase? Is a Z أقل؟ ولا Z أعلى للليد؟
الزيت أعلى للتنجستن I think.
So, tungsten كم الZ؟ Okay. هذا الZ حق التungsten 74. Okay. But then tungsten, usually I ask the student, okay, what's the symbol for tungsten? They keep, okay, it's TG, TU, whatever. I tell them, look, remember my name, W. So that's the symbol of tungsten. Okay. Lead, how about lead? Z is 82. Okay, so it's higher. Okay, so let's look at.
It's more for the lead, yes.
So let's look at what would happen actually in the spectrum. So imagine this is tungsten. Okay, we have something like this, and then we have these. So this is 80 keV. The first problem, I think the first was 80 keV, if I'm not mistaken. Yes. So if this is 80, let's do with the scale. Okay, if this is 80, okay, then probably 70 is here. So we're going to see these two K alpha lines, right? Now we're going to replace the tungsten with lead. So how is the shape going to look like of the beam? Now
I
in
think
lead,
it's going to be the same, only the characteristic lines will be shifted or change their place.
where are they going to be?
More
You're
higher
sure?
in the lead.
You're sure?
Higher, yes, they need more. We need more in it. Ah, wait.
Huh?
It's gonna be similar. We
Why
said
similar?
that we have mentioned that the inner layers, the Z has nothing with the to free an electron.
Okay, let's talk about the Brahms line. Let's forget about the K alpha lines, okay? Let's look at
Okay.
the Brahms line. So what's going to happen is that for lead, still the maximum is going to be 80. We did not change the beam, the electron beam energy. Still 80 and 80. The electron striking both targets will have an energy of 80. But this slope, remember the equation, we said that this, okay, this is going to equal to some constant C, okay, multiplied by Z. This is Z of the target, okay? Remember, it's the target. And then we have here the Emax. This is the kinetic energy of the electrons, okay, minus H here. That's the equation. So what happens? Okay, the intensity is going to be, or this is going to be proportional to Z. So when this curve is going to look something like this, it's going to be a bit higher. Okay, so we can estimate the areas roughly. It's going to be the ratio of the two. So it's 82 by 74. So that's roughly the total intensity, total energy coming out is going to. So the intensity is going to be proportional to, or going to, you know, be 70. It's not proportional. It's proportional to Z. That's for sure. So then the intensity is going to be about 80. So this is for lead. This is going to equal to 82 divided by 74 multiplied by the intensity for tungsten, roughly. Right? So now, okay, I want to come back to Husn. Your name is Husn, صح?
Yes, my name is Hussein.
Husn. Okay, now we want to talk about this K alpha lines.
Yes.
So what's going to happen?
I'm thinking about it.
Hmm.
They should change, I think.
Okay, so what's going to happen?
It's higher the Z will be higher the
So
K.
let me ask you a question.
Yes.
What's the binding energy for K shell for lead?
Mm. So you mean that it doesn't depend on the Z?
Okay, how are we going to get these K alpha lines? First, we need to create a vacancy in the K shell. صح?
Yes.
Okay. But in order to create a vacancy in the K shell, كم binding energy of electrons in the K shell? For lead. For tungsten, it's 74. For lead, what's the K binding energy?
I think it's 88.
88. Okay. So if we have such a beam, can we get vacancy in the K shell?
No, because we have 80. We
Right?
will not be able to see. Oh,
تمام. فthen actually we'll not get K alpha lines.
yes.
Make sense?
Yes, but but in the question that you put, there is the section B is 120
Yes,
kV.
in section B, yes.
Let's see, please.
Okay. So now, because this is why I'm bringing this question. I want you know, people to understand when they, okay, when this happens, what are we expecting in the spectrum? How it's going to look like? So if we have this 120, yes, then we're going to have these K alpha lines, because essentially, so this is this tungsten, we have these lines here, the K alphas, K alpha 1 and 2, and this is now 120. Okay, or even if it was 90 keV, 90 keV energy of electrons, as long as above the K binding energies, then
The
we
binding energy.
then we can actually have. So for lead, okay, what's going to happen is still this is going to increase, going to be a little bit higher. Okay, and probably we're going to have these K alpha lines shifted. So the K alpha lines, their energy will not be 88. It will be the difference between the binding energies of the K shell and the L2 and L3 shells. Okay. So it's going to be maybe around, I'm not sure the value, because the binding energies for the L shells, for lead, maybe around, for the L shells, maybe around 13, 15 keV, around 15. So if this is 88 minus 15, this will be roughly around 77. Here, these are at 59 to 60. So this for tungsten, because the binding energy for tungsten is 74. But these are lines produced transitions from the L shell to the K shell. So we need to look at the difference between the L shell and the K shell. So probably the binding energies for the L shell could be roughly around 7 or 8 keV, whereas for the K shell is 74. So the difference would give me, sorry, it's about 13, or probably 15. It's actually 15 for tungsten, because 74 minus 15, that gives me roughly 59. So lead probably is going to be higher. The L binding energies are going to be higher than that. And we just need to take the difference between the two shells. Okay. So when we look at, well, if this problem is for 120 keV, then yes, although in terms of intensity, they do not really contribute much in energies, because probably their amount is a bit, these are just two lines, but the majority of the energy will be carried out by the Brahmishan line. That's really the important thing in terms of intensity. But the shape of the fluence density curve will depend on these K shells. The K alpha lines definitely will tell us on the target. So if, for example, we have a K alpha line, sorry, if we have energy of the beam of 80 keV, probably we could not tell if this is tungsten or, sorry, if this is lead or maybe uranium. We could not tell really what the target is, but we can exclude, for example, tungsten. We can say, look, it's not definitely it's not tungsten, because we're not seeing the K alpha lines. Okay, but we cannot we can exclude, but we cannot determine what's the target material. Okay, I hope it's clear now.
It is clear. Yeah.
Okay, do I have any questions? No, this is the last slide I have. Okay, I have. So any question on this? So one is writing in the chat, هل هناك معادلة لحساب الشدة مع ايه؟ مع الفول.
Voltage.
انا عشان
Voltage.
مش ما لابس نظارتي.
Yes. Intensity with voltage.
With voltage. It's not okay. يعني معادل الحساب okay, because الشدة or intensity, the shape of it is actually governed by a lot of things. As I mentioned, unfiltered, yes, probably we can do that. But now when we're talking about a filtered filtered beam, okay, the filtration will affect what is the intensity of the beam. So I don't think there is a specific equation, but what you need to do is just get this curve and then integrate it. Look at the area under this curve. Okay, you can do this numerically. It's not a big problem. Yeah. Okay. But in general, yes, this area is going to decrease with filtration, and this area is going to increase with the atomic number of the target, and is going to be proportional. It's going to increase with the voltage. The proportionality with the voltage, remember, it's roughly around V squared. It's not just proportional. It's proportional to V squared, the potential square. Okay. Any other questions?
Sir, I have a question. If you can go, please, back to the slide, talking about the mean energy averaged over the particle fluence versus the energy fluence density.
You love equations. Oh, that's I'm happy. Okay. So let's okay, this here. Okay, so let's go back. So we're talking, which equation are we talking about?
So the curves that you mentioned,
You're talking about the example now, right?
yeah, the mean energy, where is it averaged over the particle fluence versus yes, this one, the
Yes.
energy fluence density. So you said, and actually the concept, I didn't grasp it well. And you said that in practice we use the mean energy averaged over the energy fluence density
Yes.
instead of particle. Okay, can you please explain more about it and why in practice we use this instead of that?
Okay, this will come later on, especially when we're dealing with doses. Okay, so just a quick bit of time, but let's. So the dose equation, this is given by, it's this energy fluence multiplied by the mu absorption overall. Okay. So now when we have a beam of different energies, the photon have different energies. Okay. Usually what we want to do, we want to get this mean energy.
So if you're writing something on the board, we cannot see it.
Oh, you cannot see this. I thought I'm sharing it. Oh, okay, hold on. Okay, now we're seeing, right? So the dose is given
yes.
by this energy fluence, okay, multiplied by this average of mu absorption overall. So we're ahead of time. Okay, we're not talking about what's mu absorption and so on. This quantity, usually we want to average it, want to take an average. It turns out if we do the equations, the derivation properly, then the average, the best way to obtain this average of the mu absorption over rho is by taking the average energy over the particle fluence, energy fluence, not through particle fluence. We will do this later on when I talk about this dose equation, okay? But essentially, this is what it means. When we want to grab what's the mu absorption, an average, ideally, what you want to do is you want to take different photons, you want to look at their energies, okay? And then for each energy, you need to get the mu absorption for it, and then apply this equation. Okay, we need okay. But now it's more practical. A practical way is no, we want to actually get an average energy of the beam. And then from that average energy, we go and look up what is the mean mass attenuation, mass absorption coefficient. In order to do that, we need to average. It's the correct way to do it is to take the average of the beam or the mean of the beam averaged over the energy fluence, not from the particle fluence.
Okay, thank you.
And this is, I mean, when we look at this here. Okay, a typical energy fluence of a thick target really is a straight line. Okay, in the example I gave you, it's not really what does not represent, you know, this thing, a thick target energy fluence. So that's why when we talk about the average energy, always you will hear, okay, the average energy of the beam is 1/3, 1/3, 1/3. It is actually because of the shape of the energy fluence, not the particle fluence. And the shape is roughly, it's like a straight line, almost for this unfiltered. So it's a good approximation to say, okay, the average energy of the beam is 1/3. Now, this is something interesting I've done today. Okay, and let's try to, let me bring it up. Okay.
Yeah, Doctor, regarding filter and unfiltered chart,
Okay.
I feel additionally يعني more filtered, it doesn't affect the minimal energy.
It does. The more filtration we have, okay, we're going to eliminate, you know, the lower part of the energy of the spectrum.
Okay.
Okay.
Yeah.
So, for example, we can ask, okay, what's going to happen? Let's say one question we could add is, okay, what happens to the beam, the spectrum of the beam, if we for example add thicker filtration? Okay, suppose we add a filter of, let's say, 1 millimeter of copper or whatever. Okay, and now we increase it to 3 millimeters. Okay, so the intensity is going to decrease a little bit. Okay, so we're going to have attenuation of higher energies, and lower energies will be attenuated with, you know, different attenuation coefficients. But the lower energy photons are going to be attenuated more. So we're going to expect that the cutoff energy is actually going to increase. Let's want to share this. So this is something with Monte Carlo, with EGS. So this is now, I modeled using Monte Carlo. I have a target, a tungsten target. I think the thickness I've selected was 5 millimeters. And we have an electron beam that is shooting in this direction. Okay. So we have, I think here it's 100 keV beam. keV. Okay. And what we're doing with Monte Carlo, of course, here we're going to have interactions. We're going to have these photons produced everywhere. Okay. We have here a plane. Imagine a plane in XY direction, and all what we're registering the photons that are reaching this plane. Okay. And then we're going to, based on this, we're going to then plot the spectrum of the beam or the energy fluence of the beam. Okay. So I've done this, and let's delete all of this crap. Okay, and this is how the beam looks like. Okay, or the photons, the spectrum of photons gonna look like. Okay, so this is fluence. It's actually energy fluence, not particle fluence. This is energy fluence. The units are a bit confusing. It just took me a while, you know, when I started using it to understand what's going on. Okay, but this is ME because the energy fluence should be per centimeter square. But I'm seeing MEVs here. Okay, the reason is they're multiplying the energy multiplied by the particle fluence density to give me the energy fluence density. So this is the energy multiplied by the particle fluence density. Particle fluence density has units of per centimeter square per energy or per MeV. So actually the MeV with this, they cancel out. So this is actually a spectrum. Okay, it's an energy fluence. And this is, I think the target is tungsten. This here, this is, look, this is very close to that straight line, the Brahmish spectrum. Here, this is not really due to filtration. it is more due to in the EGS, there is a cutoff energy. So basically, any photons I should have done the simulation with the lower cutoff energy, but a parameter in the EGS Monte Carlo is that any photo below this cutoff energy, just ignore it, don't track it. So photons that have energy less than 10 keV produced from the target, they're actually not tracked out. It's not that they're absorbed in the target, they're not actually simulated, not produced. So that's why we have this cutoff energy at 10 keV. Probably I will redo this, but I need to prepare the PEX data so that we have cross sections done all to 1 keV. And when I do this, you will find that actually you're going to get actually lower energy photons. But this is what's interesting is this, the Brahmachan roughly looks like a straight line. This is now we have the filtration, the inherent filtration in the target. Based on the model, I have a tungsten target. There is no, for example, it's not a full simulation of an X-ray tube. So the filtration is actually happening within the target itself, okay? So I'm going to expect that this line, if I use this line to somehow actually go like this, to fall, something like that. What's interesting, this is tungsten. These are the K alpha lines, okay? These are K beta lines. So these are happening. These are lines produced by transitions from electrons from the M or N shell to these vacancies in the K shell. So this is K beta. And these are K alpha. Sorry, this is these are K alpha lines. Okay. So these have energy roughly around 59. Okay, these will have higher energy because now the energy difference between, let's say, an M shell and the K shell is actually larger than the energy difference between a K shell, an L shell and the K shell. Okay, that's why these K betas are higher. Okay, and look here, we're getting these lines here. So these are now probably these are the L alpha lines. Okay, these are transitions happening. So basically, we're now getting vacancies in the L shell, not in the K shell, but in the L shell. And we're getting transitions from the M shell, one level above, to the K shell. So we're getting these L alpha lines here, okay? In a real X-ray tube, for example, if this simulation was repeated with a full X-ray tube with filtration, so we'll have the exit window. The window will have some filtration on the beam, and any additional filtration will also filter the beam. So essentially, these low energies, so probably what we're going to see is that the spectrum will drop like this, even lower. So we will not get to see these the L alpha lines because these energies are very low that they get filtered in the X-ray tube window, as well as from any additional filtration that we apply. Okay. But if one looks at the spectrum, they can immediately detect, okay, this is tungsten. The target is tungsten because of this thing. Okay, these things. If we look at the energies or the K alpha lines, okay. Actually, there is an option. I could turn, for example, the relaxation on and off. So if I turn it off, we will not see this. So the code itself will not actually produce these K alpha lines or K beta, this characteristic X-rays. And then what we're going to see is essentially only the Brabant photons. Okay.
Yeah, okay, thank you.
Okay, so now it's your turn, Marwa. I think you promised you're going to bring questions.
So أثناء ما كنت بجهز في الأسئلة لاحظت إنه في أسئلة فيها too much basic أنا already ما مذاكرة.
زي
أنا كنت مفكرة إنه مثلا إنه أنا أقدم suggestion if you don't mind نخلي الأسئلة تبع الامتحان في last sessions بعد ما تروح الحج وترجع إن شاء الله بالسلامة.
على فكرة next week I can do a session. يعني الحج لسه. Next week I can do a session. So probably we're going to do a session next week, and I'm going to start اللي هي photon interactions. I think everyone is waiting for this, so I'm going to start with photon interactions إن شاء الله. Okay.
يس صحيح لأن حاليا في أكثر من almost 15 سؤال هي.
طيب إيه الأسئلة عشان أنا أجهز نفسي كمان عايز أعرف الأسئلة.
أنت موجود في الجروب already؟
أنا ما بطالع صراحة هنا، بس إذا عندك
طب ممكن
أسئلة
أبحثها.
if you have a question أنا توقعت الحين أنا هنقعد كده و we're going to discuss some of these questions.
يس هي الفكرة كانت already الدسكشن بس لأن أنا حاليا ما مذاكرة 100% فأنا أخاف إنه أخذ.
أنا ما عايزك تجاوب على الأسئلة، أنا عايزك تحط الأسئلة بعدين إحنا كلنا نجاوب عليها.
طب how to share it. Can I send it to you مثلا في الإيميل بعدين أنت you can
لا
share
share it. You can actually share it if you want. تفتحيها في الكمبيوتر and you can share. I'm allowing I'm going to allow you to share the screen if you want يعني.
Yes, okay. I'm sharing it.
Okay. ذكرتني بالذي مضى محمود لما كنا نطلع الرافيكس
معطيني host disabled participant screen sharing.
أنا طيب دقيقة. Okay, go ahead. Okay.
انا وجهة نظري برضه دكتور وليد ان احنا ممكن نجمع الاسئله كلها مثلا ونخلي محاضره مثلا تبقى اسئله بس.
تمام بس
لو
انا
باقي
انا
الناس.
انا مترسد انا معاك مش مشكله بس انا مترسد to see الكويشنز الموجوده انا دكتور يعني
اوكي تمام اللي هي محضراها اوريدي. اوكي
يعني people are complaining I'm going deep in equations والامور هذه بس يعني I want to tailor هذه الاشياء I want to see so go ahead share ورينا نشوف الايكويشنز.
Okay, do you see my screen?
I see your folder.
Yes. Folder not the screen.
لا يعني الفولدر فيه الفايلز في عندك فايلز انا شايف. So open this PDF and
You see it now?
okay. Okay, the technetium M99 okay undergoes Compton scattering okay at an angle of 180 درجة in the housing of a gamma camera. What is the energy of this backscattered gamma ray? Okay, so what it's 140 kb. There is an equation لهذا الشيء اللي هي الانرجي يعني في equation of Compton energy over a photon sorry a scattered photon energy divided by the photon energy equals to 1 over نحط 1 plus epsilon 1 minus cosine theta اللي هي تطلع 180 then it's just an equation we have to know one equation. طيب we're going to this is something definitely I will cover. طيب the linear attenuation coefficient in water for this gamma ray emitted by iodine okay per centimeter okay so that's the linear attenuation. Therefore the fraction of such gamma rays that penetrate a thickness of 20 okay this is something attenuation half We know the half value layer. That's not a problem. Okay.
Mhm.
What else? So a thickness of 12.6 centimeter of water would reduce the intensity of photons emitted by كده to what percentage of the center? Okay. We know the thickness, we know the half value layer, then we know the reduction in intensity. That's an attenuation law. اللي بعده. X-ray absorption and transmission depends on patient gender, patient age, patient weight, body part thickness, and composition. Probably it's the D actually. Okay.
Mhm.
أشياء X-ray beams with energies in the KEV range yield better visualization. هذه الستة كلها شكلها diagnostic. X-ray beams with energies in the KEV range
Correct.
yield better visualization of skeletal anatomy than X-ray beams with energies in the MEV range. Because, okay, okay, it's probably because of anything photo effect. That's something, you know, for imaging. We want that. Okay, so probably B is the correct answer. Per production, okay, we don't have this in the KV. Per production, imaging detector for KV have better spatial resolution. That has nothing to do with that. MEV X-ray imaging system have larger focus, but that has nothing to do with this. So basically, it's because of this photo effect. A 40 keV X-ray undergoes a photoelectron interaction. Okay, so this is a photoelectric interaction with a hypothetical atom having electron binding energies of 20 and 50 keV. What are the possible kinetic energies of the resulting photoelectrons? So this is 40 keV. Okay, if the binding energy is 50 keV for an electron, then it cannot actually knock it out. It can knock only the 20 keV electron. This 40 keV X-ray. This is the photo effect. So it can knock out this 20 keV. So the electrons, when it's going to absorb actually the 40 keV from the photon, and when it comes out, it will come out with an energy equals to the photon energy minus the binding energy. So it needs to use or spend out 20 keV to overcome the binding energy. Therefore, the energy that comes out is 20 keV. Okay. هذه كلها أشياء we're going to cover actually. It's good. يعني أنا أشوف الأسئلة هذه. Okay, photo effect. هذه okay, the most common interaction of tungsten gamma ray in water or soft tissue. So this is Compton. Okay.
Okay. Yeah.
Anything in soft tissue except mammography, actually حتى في diagnostic range, 50 kV, it's the dominant interaction in water is actually going to be Compton
Really?
scattering. Based upon the figure below, okay, this X-ray energy would yield the optimal mammographic contrast. So this is something, it's not really the physics, it's more related to the equipment. In mammography, we want something around 20 keV. So we want the energy to be around 20 or 25 keV. So based on the figure below, a 20, okay, would yield the best. Or we're looking at the best contrast actually between, you know, between these two composition there. So the best contrast is probably going to be between the two materials with the highest attenuation coefficient difference or linear attenuation coefficient difference. So it's going to be 25 kV. Anyway, for mammography, it's always low energies, 25 or lower actually. That they
Yes.
used because we want actually the best contrast. Okay, next.
Yes.
120 kV particle has a range in soft tissue of 100 microns. Okay, yielding a mean LET of, I'm not, so this has a range. Okay, so the mean LET is basically we take the particle energy divided by the distance it travels. It's the average LET. Okay, so 120 divided by 100, then we get 1.2 keV per micron. This is the answer.
Okay.
So this is the average, you know, LAT is similar to stopping power. It's just a linear energy transfer. Stopping
Yes.
power is a mass energy transfer.
Correct.
Okay, this is part we're going to talk about it after we do the photon interactions, when we deal with the electron interactions. Okay, pure beta particle emitting radionuclide are best shielding using, okay, should we use lead, steel, titanium, zinc, or plastic? What's the best shielding for beta particles. This is something related to what we have been discussing, the Brahmi-Shannon. Okay, so if we have a higher Z, we get more Brahmi-Shannon, right? So if we were talking about shielding, we want to have lower Z material. So plastic is probably the right answer. It has the lowest Z.
Yes, correct.
Okay. انت
Yeah.
بتختبريني شكلك ها؟
No. I'm thinking إنه
طيب a 60K
البيتا
okay, a 60 keV or J electron. Now understand what's a J electron. Has a range in soft tissue of 0.3 microns, yielding a mean. Okay, the same thing. We take an energy divided by the range. Okay.
Okay.
X-ray produced by the scattering or stopping of charged particles are called Brahmi-Shannon, right? So it's Brahmi-Shannon.
Okay. Mm.
If one attempts to count a sample containing 10 microcuries of tritium, a very low energy pure beta emitter, in a scintillation well counter, the observed net count rate. Okay, this has to do with counting statistics and so on. I'm really, this is something I'm not, يعني ما متذكرة, bottom line, okay? But if one attempts to count a sample containing 10 microcuries of tritium, a very low energy beta, in a scintillation well counter, the observed net count rate. So, but anyway, the observed count rate, I'm not sure about, because this is something related to the detector, specifically to the detector. It's equal to 0, meaning we don't get anything, or equals to the true count rate. This is very low energy pure beta. If this has a very low energy, I'm wondering, can it actually ionize the scintillation detector or not? Can we get photons produced or not? So maybe there's something tricky about this question. Okay, I'm not sure what is the energy, the mean energy for scintillation detector in order to produce photons. And I'm not sure if the tritium is capable of actually producing or ionizing, producing photons. I'm not sure, to tell you the truth.
Okay.
The most common, this is, I think, nuclear medicine. They probably know this better. The most common interaction of technetium-99, gamma ray. I hate technetium-99. Okay, we want iridium. We want cobalt.
Okay.
Okay, gamma ray in water or soft tissue, the most common interaction. Okay, in tissue again, it's Compton, end of story. Okay, I think, see, this question is repeated. Which of the following would yield the greatest production of Brahmi-Shannon? Brahmi-Shannon, we want to have a hydrogen 3 endpoint beta range energy. That's the energy. So with the Brahmi-Shannon, it's probably energy, right? So strontium, this has strontium. Oh, no, we have here phosphorus 32. So we have the maximum energy of beta particles 1.71. So this will produce, we will have the greatest production of Brahmi-Shannon. It's related to the energy. It's like, well, this actually is basically what we've been talking about, is that the intensity of Brahmi-Shannon, okay, is a function of the energy of the particle. Okay, or it's the function of, it's function of the energy of the particle. So we would expect that C will have the highest actually Brahmi-Shannon produced, because the betas will have the highest energies, 1.7. Okay, next. And this question is an application.
The strontium?
No, it's the phosphorus.
The phosphorus.
Because the beta produced has the highest energy, 1.7 MeV compared to strontium, right?
Yes.
So this is something we covered in today's lecture, that the intensity will increase with the energy of the electron.
Correct, yes.
Okay. So the interaction depicted in the figure below is what's this? We have X-ray, this is an X-ray, and then we have an electron coming out. Low energy, what? This is a electron. Oh, this looks like Compton, because low energy photon, and here we have a recoil electron. So this is Compton. Next. Which of the following would yield the greatest production of Brahmachan? Again, that's the same question, okay? We'll just look at the one with the highest energy. Among the following types. شوفوا الأسئلة هذه يعني كلها okay very quickly الواحد يقدر يجاوب عليها. ما فيها حسابات ما فيها. It's based on basic concepts of physics. Among the following types of interactions of X-ray and gamma rays in matter. Photoelectric effect, Compton, pair production, and photodisintegration. ايش الفوتوديسنتجريشن؟ ايش هذا
I don't
الانتراكشن؟
remember.
ها؟
I don't remember.
Okay, something we're going to cover. Okay.
Okay.
في طبعا really photodisintegration basically a photon interacts with the nucleus directly absorbed by the nucleus, and then the nucleus can emit a proton, can emit a neutron. It's a nuclear reaction. This is what we mean photodisintegration. Okay.
Okay.
Which can occur for photon radiations commonly used in diagnostic radiology. يعني الجماعة دول حاقرين بينا احنا بتوع الراديوثيرابي. ما بيجيبوا اي شيء في الراديوثيرابي. طيب types of interaction. Okay. Which can occur for photo radiation commonly used? Okay, of course it's going to be Compton and photo effect. You just have to look at the numbers there. Okay. A 80 keV X-ray undergoes a photoelectric interaction with a hypothetical atom having electron binding energy of this 10 and 50 keV. What are the possible kinetic energies of the resulting photoelectrons? So again, 80 keV can interact with both electrons, right? So we can have 30 keV and we can have 69 point something, I think, or 70 keV. Okay. So here I think 10 point.
So it's 30, 45, and 70?
No, I don't think it's, sorry, yes. So this is the binding energy. So we're going to have 30. It's not this 30.1. I think it's 30. I think the numbers don't make sense because it's just the difference. 80 minus 50 is 30. And then 80 minus 10.35, this should be roughly around 70. So seems something wrong unless someone can catch something that I'm missing from here.
It's not 10.35, it's 10 and 35 and 50.
Oh, okay. لازم ألبس نظارتي إذا. Okay.
Okay.
Okay. So then, okay, we're going okay. So 80 minus 50, we're going to have 30. Okay, it can happen. It can actually ionize it. And the photoelectron is going to be 30 keV. Now 10 minus 35, that again 45. Is going to be 45, right? And then 80 minus 10, that's going to be the 70. Okay.
Okay.
معلش أنا ماني شايف كويس.
No
طيب.
problem.
Okay, something is the predominant interaction for X-rays commonly used in CT scanner in soft tissue. Always Compton scattering. هذه الإجابات هذه هل أنتم عارفينها ولا لازم يعني لما أجي أتكلم عن interactions we need to understand why.
هي الأنسرز already موجودة في الرافيكس بس it's not always we understand why. خاصة لما يكون فيها calculations.
Okay, ما في ولا calculation إلى الآن. أنا شايف calculation. يعني something that needs a calculator. كل حاجات يعني can do it mentally. طب X-ray beams with energies in keV range yield better visualization of. هذا مش كنا جاوبناه. It's just a repeated question.
Yes, it is a repeated
Okay.
question.
A 60 keV X-ray undergoes. Okay, هذا برضه جاوبناه.
20 and 10.
So here we have
Yes,
20 and 10.
10
We
and
can
20.
have actually for both, right? The SI unit for dose equivalent and effective dose is طبعا اللي هو سيبرت.
Effective dose Siebert. Yes.
Okay. يعني ممكن سؤال زي ده the SI unit for let's say the particle fluence or energy fluence. Now we know, for example. Okay, something is the predominant type of interaction of 100, okay, gamma ray in soft tissue. Anything, okay, like this diagnostic is going to be Compton. The image contrast between bone and soft tissue in the radiograph shown here is primarily due to this is the photo effect. This is why we're getting this difference, image contrast. because with photo effect, it's proportional to Z to the power 3. That's why it's just a very good contrast.
alright.
اوكي خلاص كده. اوكي
Yes,
الأسئلة
absolutely.
سهلة يعني. اوكي غطيناها، فخلاص ممكن we can skip photon interactions, we can go to electron interactions.
إن شاء الله. Okay, yes.
اوكي لا I think الأسئلة يعني probably الأشياء theoretical I'm going to cover. Okay, a lot of this I'm going to even go for more details. لأنه basically الكورس هذا يعني الأسئلة هذه really it's for a level not for physicists, it's more like for therapists, for physicians. أنا الحين الكورس that I teach residents, I actually pick up the questions from reflex. Okay, لكن الphysicist needs to know more than that. Okay, we need to not just to memorize the answers, we need to and one thing نصيحتي لك, this is how we learn physics, is we memorize graphs. We don't memorize equations.
Yes, yes,
We
correct.
memorize the graphs. Okay.
Mhm.
We know the equations, derivation of the equations, what they mean and so on, but really we know the graphs. Actually, this is يعني كانت في عندي colleague في ماجل يعني أول ما جات هي خريجة ويسكونسن، فكانت تقول يعني في البورد اكزامز مثلا بيجيهم أسئلة إنه والله إيش الاتنيويشن كوفيشنت مثلا in lead for let's say 1 MeV or so. Okay, or the mass attenuation coefficient. فتقول يعني احنا we had يعني when they ask this for a graduate of McGill, they actually draw the full attenuation curve with respect to energy. And then they tell the examiner, pick the energy you want. It's not just for a specific energy, but this is how we were taught. We needed to memorize these things. And it made a difference, to tell you the truth. في مجالنا مثلا دائما الطلبه الجدد يقولوا اوكي ليش لازم نحفظ، ليش لازم نسوي والامور هذه كذا. Remember, انتوا او احنا we actually work with physicians. Physicians طبعا حفيظه يعني من اكثر مننا for sure. And they memorize stuff. It's going to be very embarrassing if they going to beat us in physics. Very, very embarrassing to us.
Yeah, no doubt.
فعشان كده ما في حكايه okay, we need to memorize stuff for sure. Okay. Anyway, I think it's الساعة 10 جات. Okay, so I hope you enjoyed today's lecture. And we're going to see you inshallah next week. So I'm going to start with photon interactions. It's going to take a few actually lectures because I want to go deeper in details. I'm not going to talk about just the attenuation coefficients, but I want to talk about the differential cross sections in order to understand what happens with angles and so on. So inshallah, we'll start this topic next week, and then we'll take it from there. Okay, but I hope to bring questions like this. If you want, we can always have a half an hour for questions like graphics, things that you're seeing coming in exams. Then we can actually dedicate. But many of the questions, I'm happy to see many of the questions that at least the part that I've covered in terms of Brahmacharanga and so on, it makes sense. It will enable you to answer these questions without really memorizing اللي هو السترونشيوم والphosphorus. Just very simple. Highest energy, highest Brahmacharanga. End of story. Okay?
Okay, yeah.
Okay.
يا دكتور, I want to ask just a general question about medical physics.
Okay.
بخصوص الريزيدنسي بروجرام. حاليا الاكريديتد ريزيدنسي بروجرام هو فقط تبع الكامبي accredited hospital I think. Is there any other centers مثلا هي ما كان accredited بروجرام ممكن تسجل ريزيدنسي بروجرام للميديكال فيزيكس؟
تكلم انت الحين في نورث امريكا ولا وين انت؟
No, من قطر.
Okay. صراحة I'm not sure if there are residency programs, but usually in the States even if it's a residency program, yeah, just starting on and so on, they will probably want to meet the criteria of campus. So maybe suppose a hostel today started a residency program, probably it's not going to be accredited immediately, but they will make sure that, okay, at least this residency program complies with CAMPEP. And when they have their first batch of graduates and so on, then they will actually apply for accreditation. Or some centers, they actually have some collaboration with programs that are accredited. So the problem in North America, I think, is residency programs probably it's going to be difficult for someone who's not a graduate of from a CAMPEP
Yes.
uh,
Educational program.
to enter it. Some residency programs might offer, this is what you should be looking for. Some residency programs might offer actually these courses for CAMPEP certification. I know, for example, at McGill, I don't know if they do it, they continue to do this or not, but a resident who is not graduate of a CAMPEP educational program, they will still give them an opportunity to attend courses. I think you're required to take 4 courses so that you can obtain a certificate, a CAMPEP certificate. So this is a way that they do this to bridge, for example, because often you have a PhD, someone graduated with a PhD in physics and nuclear physics and so on, and they want to actually enter in the field of, or they practice in the medical field, medical physics field. So they will need to actually take these programs, okay, this physics. If you take the physics course at McGill, okay, now what I've been teaching you, you're halfway through. You should be able to يعني
Consider it. Yeah.
yeah, to pass it يعني for sure. Okay.
لأنه حاليا ال ABR exam هو محكوم بال 2 years residency.
Yes.
فأعتقد إنه هو جدا محدود، يعني الفيزيست ما كل الفيزيست يقدروا ياخدوا ABR certified، ما يكونوا certified
صحيح.
إلا إذا كانوا هم متخرجين. بعدين أنا شايفة مؤخرا إنه بقى يعني بارت مهم من الجوب ديسكريبشن تبع